Okay, so let's start. Hope you had a good Thanksgiving. I have some announcements to make, but I'll wait for that until more students trickle in. But let's start on current topic. So we had started looking at synchronizing multiple clocks last time, and sort of I described why in some of the applications then having network nodes have a common notion of time is desirable. And then sort of the very first approach that I wanted to go after was that synchronization can come in many different forms. And in one case, it could simply be that I want to synchronize in a logical sense. So different nodes may not be able to measure passage of time in terms of seconds or whatever unit of time you have, but they could nevertheless reconcile the order in which important things happen at different nodes. And now, if that's all you need, in many applications, it's ordering which is important, like this process access before some resource before another process did. If that's all you are after, then if you had synchronized physical clocks, then that would be an easy way of doing it. I mean, if we all had accurate clock, let's say GPSs, then you can basically kind of just look at the timestamps and be done with that problem. But these kind of accurate clocks are relatively recent, and also in many cases, the clocks are still not accurate enough to be able to get the order right. So you do oftentimes sort of you do need to use some other approaches to get a logical time right. So some of the early works in clocks and clock synchronization took place in theoretical computer science with the goal of getting event ordering correct. So what's happening out here is I have a system with 3 nodes, P1, P2, P3. Each one of the E's indicate different events that are happening, and we want to get some sort of a partial order between them. And the only thing that we have access to is that whenever an event corresponds to sending of a message and reception of a message, so like this event out here, ET3, then we can certainly say that by pure causality, the reception event has to follow the sending event. And using that, one can kind of build a whole clocking structure. So the main thing is that we have the causal relationship, that something happened before something. And what we want is that if my physical clocks were synchronized, then if an event happened before another event, then its timestamp would be earlier than the timestamp of the subsequent event. But without physical clocks, we want to get this kind of sequence going. So the idea in sort of these approaches tends to be is that we will assume that reception and sending of messages are events. And that sending causes reception. So the relationship that we have, the right-going arrow for causality is there. So basically what it gives is that there are some sort of common sense rules which will apply. If A and B are events on the same node and A comes before B, then we will know that A happened before B. So at any given node, you can certainly just timestamp according to its local counter, and you will get the ordering right, even if that local counter has no relationship with a correct notion of time. At least you get the ordering right. If A is the sending of a packet by one node and B is the reception, then also I will get the causal relationship. And finally, it stands to reason that if A comes before B and B comes before C, then A comes before C. So these are 3 common sense rules that you can build upon. Then we basically say that 2 nodes are concurrent, that is, they took place at the same logical time. If A happened before B and B happened before it, that also kind of stands to reason. And then finally, the partial ordering is the irreflexive partial ordering also exists. That is, A happened before A, or A is concurrent with A. Okay, so now using these basic insights, you can build up a logical clock. So what is a clock? Well, clock is a way by which I have to assign a timestamp to these events, a number to these events. So imagine that at each node, I have a clock Ci. So each node has its local clock. And what this does is that using that clock, I assign a number to an event that happens at that node. So if the event A happens at node I, then we'll look up at that local node's clock and assign a timestamp to that event, which would be the Ci, the value of that counter Ci at that time. And what we are looking for is a global clock. So the global clock C is called C, and what it does is it assigns to any event B the number CB, where CB is what the jth clock said if B happened at node J. Okay, so nodes assign look up at the counter, and then the global clock basically says, you want me to timestamp an event, let's see which node it happened at, and we'll just make it correspond to that node's clock. Now, these logical clocks, you can argue, are correct if I were to now somehow make use of changing the local clock whenever a message reception happens. So basic intuition is that whenever a message arrives, then I'm going to attempt to timestamp it using my local clock. But that message will also carry the timestamp of the sender's clock. And if my local clock is behind my sender's clock, then I'm going to make it advance. Okay, so the idea being that I have to make sure that the sending happens before reception, and therefore, if the sender's clock was ahead, so when so the timestamp it would carry, the sending timestamp would be ahead of my clock. So what I'll do is I will advance my clock whenever I get a message carrying a timestamp which is in the future relative to my clock. So that's so that's the basic thing that we will do. So the strategy which comes down to is the following: that if two events are happening at the same node, clearly the causality or happens before condition is always satisfied. If we have a sequence of events such as sending and reception, then what we need to make sure is that the timestamp that was assigned by the sending node is less than the timestamp that is assigned by the receiving node. And to do this thing, to achieve these things, so basically our strategy would be at any given node, whenever I see an event, I increment the counter. So you can think of your clock as an event counter. And to meet the second condition, what we do is that anytime we receive a message, and if I were to simply increment my counter and then assign a timestamp, if that timestamp does not meet this criterion, then I'm going to further increment my clock so that it is at least CIA plus 1. So clocks jump, clocks increment every time there is an event, but clocks also increment every time there is an incoming message which carries a sending timestamp which is ahead of my clock. So I sort of increment this thing. So synchronization wise basically boils down to anytime anyone tells me, hey, time on my clock is this, and I see my clock is behind, I'm going to increment my clock. And everyone is kind of playing the same game. And it satisfies kind of the two properties which, at least for purposes out here, one needs to have, namely getting the logical ordering right. Now, it obviously doesn't, it will classify things at concurrent, that is, things may have same timestamp, even though in physical time they may have happened in some other order, but because here we do not have sufficient information. But this is how these kind of clocks, logical clocks, is how a lot of distributed protocols work, which is they basically try to reconcile whether the ordering in which things are happening. And for many purposes, this is sufficient. Now, if you want to get a total ordering of events, that is, you really want to assign these things in order, then you will somehow need to kind of get additional information. That is, what this will do is it will not be able to discriminate among events. So if nodes never exchange messages, in a degenerate case, if nodes never exchange any messages, then each node would increment, and depending upon how many events are locally happening, their clocks may go, maybe the numbers on the clocks would be totally out of sync. So what we need in many cases, therefore, is synchronization, which can achieve total ordering by essentially relating every node's counter to a common notion of time. That is, we need a physical notion of, or universal notion of time. So I mentioned previously that GPS is one of the one such technology, which is in the process of it calculating its GPS receiver's location. GPS also has to estimate the time. And the way it kind of works is that every satellite has an atomic clock, which are kept in sync by sending messages from the ground. So satellites know their position also because of orbital mechanics. So we have basically a bunch of nodes which are time synchronized and whose locations are known. And then they send out a signal, and then locally the node has to figure out where it is, but in the process of figuring it out where it is, it also has to figure out what time it is, because it has to, the basic strategy is that it estimates the travel time that the signal had from each one of the satellite, and then once I have the travel time, then I have a travel distance with the speed of light, and then each such measurement relative to a satellite puts me on a sphere centered at that satellite. And then by taking in a three-dimensional space, you need at least 4 satellites to disambiguate where you are. And even then, because of measurement errors and all, the 4 spheres will not intersect at a single point. So you will have some sort of a volume in which you will narrow things down, and then you use optimization techniques to find what's the most likely position. And usually, then you use additional satellites. Receivers can go to as many as 12 satellites to figure that out. Now, to do this, to measure the travel time, in effect, they have to first estimate time here. So the equations that get solved are in 4 variables, x, y, z, and t. And then locally, these GPSs, they use some stable clock source, usually a TCXO, because otherwise what happens is, as you are making multiple measurements, your local, the standard crystal oscillators are too drifty to get you accurate location. So one of the reasons TCXOs are used, one of the things I used for in our devices is indeed the GPS receiver. So GPS gives us, has to internally calculate time. It doesn't always expose it. So most GPSs would expose it through some sort of a serial port or just display it, but that's too inaccurate, because by the time you get to read the clock, some amount of time has passed. So many GPS boards, if you kind of buy the raw versions of them, they will have a pin where they pulse the pin every 50 nanosecond, or sorry, every second. And the idea is that 1 second is aligned with the UTC 1 second. So every once you have essentially a ticking signal at 1 second boundary coming out of all such GPSs which have that kind of pin, and they would be synchronized to the same degree, ideally to the same degree as the GPS satellites are. Now, having said that, there are of course lots of inaccuracies. So firstly, GPS does not mandate any specific algorithm. So more sophisticated GPSs do use more sophisticated algorithms, making use of some additional information. So that's one part of it. But the other thing is there are errors because the speed of the radio signal varies through the environment. Okay, so it's we know the speed of light in vacuum, but the signal here is cutting through layers of atmosphere, and sort of the characteristics of the density along the way is going to affect things. So there are all sort of radio effects which kind of come into the way. There are relativistic effects which come into way. But at the end of it, sort of, it's very realistic that if you have a running GPS which is already locked in, then you can get this signal once every second, which is within plus minus 50 nanosecond or thereabouts of any other GPS, similar GPS anywhere else on the planet. And with military grade stuff and all, you can go down even finer. So that's a great technology to have. A lot of pros. I mean, obviously, getting this level of accuracy takes care of so many applications, as you can imagine. The cons are it doesn't work everywhere. It doesn't work indoor. If something goes bad, then the delay is a lot. If you lose lock with the satellites, then you have to hunt for them. Power, cost, all those kind of things. And the other part, like I said, is not all GPS receivers are designed for time. So if you might say, hey, I have a GPS receiver with a serial port output, it's spitting out time information, I can use that. Unfortunately, serial port kind of negates most of that.
For these receivers, is there like a licensing that you have to use them, or as long as you have the hardware, you can use it?
Exactly. So in this case, the manufacturer has to get the thing FCC approved. The end user don't need to. Yeah. The way FCC licensing works is that in some when they say something is free to use, that means the end user doesn't need to get the license. The manufacturer still needs to. So like Wi-Fi, for example, you can use it. You don't need a license, but Apple or whatever, Google, whoever device you're using would need to get that license. Okay, so GPS is great. And by the way, kind of the point that you made is important, because even though GPS is a receiver, you still need to get it licensed, because any circuit which is receiving these kind of signals and all is going to make emissions. and they want to also make sure your device is not emitting unnecessarily. Okay, so even though GPS strictly is a receiver, you might say, hey, what's the harm? I'm just kind of receiving it. Now, having said that, let's say you were to prepare your own receiver to do this thing. As long as you're not selling it, no one is going to come after you, because FCC will come after you only when you transmit something. If you are designing a GPS receiver in the lab and testing it out, it's fine. The only time you need to get it licensed is when you put it into a product and decide to sell it. Whereas, on the other hand, if you rig a circuit and decide to transmit on it, then you are supposed to get the license. It's a different thing that almost any group working in this thing at times, I mean, you can buy these software-defined radios, and in fact, some of the groups, project groups are doing that. We are all technically violating FCC, but no one detects.
So like as a developer, you need to get access to satellite, or all the satellites are up there for you?
For this, for GPS?
Yeah.
So firstly, I guess GPS has almost become a noun, even though technically it is a specific system operated by the US. There is also Galileo, and there is GLONASS or something like that, and then there is a Chinese system. So there are three other systems: European, Russian, and Chinese. And you can certainly design. They are all open, or they all have open bands, but they also all have encrypted bands also, which obviously there is for the militaries. So like, for example, the US GPS has sends out an additional signal, which is an encrypted signal, which only the military receivers have access to. And actually, with full-blown access and all the advanced algorithmics and all, you can get down now to sub-centimeter accuracy. So it's pretty amazing. I mean, you can have things located to the level where you can have an autonomously controlled helicopter land on a rocking ship on ocean, and they kind of successfully manage it to do it. Okay, so they use it for surveying and all. I mean, basically down to millimeters you can do it, but these are like $50,000 GPSs and only for military purposes and stuff. And of course, correspondingly, the time is also accordingly accurate. Okay. So anyway, so that's kind of nutshell why GPS is great for timing. And again, consumer grade GPSs, you can buy boards from SparkFun or Adafruit and all. They can get you to, let's say, a few small number of tenths of nanosecond once you have the satellites locked in and all. Otherwise, it takes time. You cannot kind of just power it down, pick it up, and say, hey, tell me the time to 50 nanosecond accuracy. It can't. Okay. The other very common service, which actually when you see these radio ads and all, they say atomic clock accuracy. Okay, they will be selling these wall clocks and wristwatches and all. Okay, so what are they doing? Well, they usually rely on this radio signal transmitted by NIST. NIST is the National Standard Bureau for the US. So what they do is that, and they are the one who maintains US's time. Okay, so the atomic clocks are maintained by NIST, particularly in Colorado. There is a big setup. They are the group to go with if you're looking for newer timing technologies and stuff like that. What they do is they transmit the standard time over radio waves, essentially your AM, FM, shortwave type radios. And what happens in this case is they have a very high power transmitter, 50 kilowatt, which depending upon conditions either covers much of US or at times also kind of goes well beyond US territory. So day, night kind of transmission differences happen. What carries on this signal is BCD coded time information. So essentially it's saying time is blah, 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 blah. And then repeating the same thing again and again and again. And it's binary coded decimal, those following. So year, day of year, hour, minute, second, some flags indicating whether it's daylight saving time or not, leap year, leap seconds, all those kind of things are kind of transmitted. And obviously the thing out here is what is happening is somewhere in Colorado the radio station is saying time is this. Okay, by the time you are receiving the signal here in Los Angeles, of course some time has elapsed, right? I mean, and that depends upon the distance. Coast to coast, speed of light will carry has a delay of around 20 milliseconds or so. So you have to either have some mechanism to kind of rule this thing, compensate for this delay, or otherwise kind of live with this thing. Okay, so because that depends upon where you are. they also send a signal over telephone, over cell phone, stuff like that. And obviously, the quality with which you will be able to get the time is going to depend upon what kind of, best cases using these shortwave radios. But if you're doing via phone, then the networking delay through the phone stuff nowadays is packetized, often sent over the internet. Depending upon whether you have voice over IP type telephone, it might be different. So by the time the data comes to you, may have gone through some delay. So 30 millisecond delay with landline, 100 millisecond with cell phone, 250 to 500 millisecond with satellite connections, and so on and so forth. So you need to kind of correct for these things. There are similar other services available from other countries, and kind of you can even have worldwide access to this thing. So this is another obviously very cheap thing because the receivers are much cheaper. These are essentially kind of shortwave or AM type receivers. You can buy them sort of again from the usual places. These tend to be lower power than GPS. These are just simpler devices, but obviously far less accurate. So why not put such a receiver at every node? Well, again, issues come down to outages and all. These are going, those of you who have ever played with shortwave radios and all, you know atmospheric conditions affect them quite a bit. So all those kind of things happen. But the flip side is they are for their purposes. I mean, if we can have wall clock, which are always half a second accurate, or our wristwatches are always half a second accurate, that's great. And they typically can do better than that. Okay, but you do have a radio which is listening all the time. So not necessarily kind of cheap. So, but for wall clock type applications and all, this is essentially your oscillator. Okay, you basically just have this radio thing, and it's just advancing kind of the clock mechanism. Okay. Now, these were deliberately shaped signals or deliberately sent out signals just for purposes of timing or timing and location. You also have access to other sort of timing information, which is opportunistic in flavor. So a lot of systems around us have periodic signals in them, and those periodic signals are kept very, very stable for a variety of reasons. So one is the AC electricity. In this country, it's 60 hertz, and it's kept very stable because it's kind of a universal agreement among all the generators who are hooking up to a grid, saying, hey, we all agree that we will remain at 60 hertz, and we'll strive to be at 60 hertz, because if the load increases, then there is a tendency for the load to pull down the frequency of the generator, and that translates into the rate at which the rotor of the turbines are rotating. So if the load increases, that more mechanical energy has to be put to keep it in. If generators start going out of sync, bad things happen, the blackouts happen basically. Okay, so there are websites where you can monitor real-time frequency of a grid. Okay, I know there is for UK like that. I don't know if there is one for US, but you can see kind of in UK the frequency is 50 hertz. You can see kind of the needle kind of just hovering around 50 hertz. It's long-term very stable, short-term less stable. So going to our Allen variance, as Allen variance is high short-term, but Allen variance is pretty darn good over a long-term basis. One can exploit this thing, and the nice thing about AC is that it's literally everywhere. All you need is a smart enough, sensitive enough circuit, and you can pick up the signal from just the wiring in this room. Okay, so power companies try to do this thing, and you can design the circuit. There's an example out of CMU. You can see a very tiny little board. Essentially kind of a little microcontroller together with a LC circuit, and 58 microwatts, and they get a millisecond accuracy over 11 days. Okay, so of course the idea out here is AC signal is just getting you the frequency, right? It's all it is saying is that you're synchronized with the grid. It's not telling you what the time is. So you do need some node which has a notion of time, but then all other nodes can. So what you can imagine is that, let's say I want to get nodes in this building synchronized. So firstly, if all I want to do is have them be synchronous to each other, I can just have all of them pick up the AC signal and be done with it. If I want them to have a notion of time, then what I can do is I can have some other mechanism so that I can communicate with these nodes to tell them the time. So do kind of a one-time clock offset correction, but then after that they live off these relatively stable oscillators. So you could imagine doing this kind of stuff. This particular project that they had done, so they were using this thing for synchronizing sensor nodes and all down in coal mines, so which is pretty deep inside the earth. So GPS doesn't work, WWVB doesn't work and all, but the AC signals are there, and so they kind of made use of that. Could you think of other examples where timing information is out there? very stable periodic signals that you can pick up on. No thoughts? Television, frame rate, right? So the NTSC signal transmitted by all the TV stations are insanely accurately synchronized. What else? I gave you one. Say something else. Cellular signals. Cell phones, base stations are insanely synchronized because otherwise they'll be trampling on each other's bandwidth. Okay, so in fact, there is usually an atomic clock in the base stations or something equivalent. Okay, so you can go off that. Another one actually is 802.11 itself. What 802.11 does is, again, the original 802.11 protocol had no notion of time synchronization or anything like that. Well, it was in the standards, but no one used to use it. But there was always this mode in 802.11 where the idea was that we'll create time slots, and then nodes which want to talk to the base station are going to transmit according to some time slot. And to maintain that time slot, you needed to maintain a common notion of time. So there was a timing beacon which is sent out by the base stations, by the access points rather. And the way it kind of works is a little bit like WWEB. Basically, like the base station says time is X, everyone else receives it, and they say, aha, okay, my clock fell behind or is ahead, you correct my clock. Okay, and that's what it does. And for what 802.11 was meant for, which is 100-meter, let's say 200-300 meter type distances, the speed of light translates into a relatively modest type error, so you can kind of live with it. So it doesn't get you kind of like nanosecond type errors, but it still gets you something which is pretty decent. Okay, and again, the key thing that you would see is that all of these one-sided schemes are able to get frequency, but they never, but they're offset, namely, so they're not exchanging any time information, firstly, in cases like the AC. And if they are doing time information, that is, if the sender is sending out, say, time is this, then that timing information is always off by whatever is the propagation delay, and that propagation delay you can upper bound, but you will never know accurately if all you're allowed to do is a one-way communication. So for one to be able to get the clock set accurately, you need one of the two things. You either need to know very precisely what the propagation delay was so that you can subtract it out, or you need to have a two-way handshake. Okay, one of the two conditions have to be met. Okay, so in that vein, sort of NTP, which is the network time protocol used in the internet, it is an example of a two-way messaging. So what happens there is that out somewhere at some nodes on the internet are some very accurate clocks. Okay, these are usually called time servers. I mentioned last time that there is this machine at UCLA called time.ucla.edu, and there are similar things. There is time.apple.com, time.microsoft. So a lot of these companies name very obvious names. So those are the layer one, very accurate servers which have atomic clock accuracy. And then there is a hierarchy of things. So the idea is an end node like my phone or laptop, it kind of talks to its local time server, which in turn talks to a layer above and a layer above. They call them strata, or so strata 1, 2, and 3. And the handshaking that takes place out here is a little bit kind of bidirectional. So the idea is a node which seeks to know the time, what it will do is it will contact a server. It could be a Stratum 2 server, or could be a Stratum 1 server if you are lucky to be close to it. You send a message, and then it bounces back a message. We'll talk later how kind of the process works. But the idea is that when we are sending the messages, each party, the sending party timestamps the message, the receive party timestamps the message. This round trip gives you a few timestamps, and then you do some algebra on it, and it turns out that you can get both time and propagation delay. Okay. In case of internet, you kind of need it because the delays through the network can be pretty variable and a lot more. I mean, because a big part of the delay is the delay that takes place in routing and switching the packets. So NTP conceptually then, level n synchronizes to level n minus 1, level 1 synchronizes to universal time via GPS or some such mechanism. Usually nodes seek timing information in multiple things, so what you can set your laptop to do is to contact multiple servers, get time information from them, and then get rid of the outliers, average the rest to get a more robust notion of time. They do also very sophisticated modeling and filtering and stuff like that in this. Kind of the idea is you might want to weight the information from different sources by how good they are. You attempt to model the clock drift so that you can compensate for it. You attempt to model the network delays. So the algorithms used in this thing are pretty complicated. So there's a lot of signal processing control stuff goes on outside the detail of a course like this. But point is that with all of this magic, despite a pretty flaky networking environment and despite sort of pretty bad quality delays over the network and all, NTP kind of works out pretty well. It can easily get you into like sub 100 millisecond accuracy and perhaps down to a few tens or even single digit millisecond accuracy, but it takes a lot of time. We have billions of nodes on the internet. You don't want all of them blasting out this traffic, so the traffic is controlled. The rate at which you contact the time servers is limited, and so it takes some time to convert. So you start a laptop, it will get the time, and then over a matter of days, if you leave it running, it will get progressively more kind of accurate. So NTP as a there's a guy called David Mills, a professor at University of Delaware. He's kind of the father of NTP, and there are standard software releases now that for every known operating system. It's essentially a messaging protocol. As far as NTP is concerned, the magic of what goes on inside out here, I mean, you can have more and more sophisticated algorithms, but there are open source variants kind of floating around. So one thing is NTP Daemon, but the NTP Daemon is kind of client side of this thing. You can download it, it's open source, available for most operating systems, and you can basically, as long as you're on the internet, you can kind of get synchronized. Problems that happen is that NTP servers may not be good quality, the path to them may not be good quality, your own timing information, your own crystal oscillator may not be a high quality one. So all these factors which kind of come into play to affect things eventually. So NTP, nice thing, readily available, industry standard, pretty good if you're looking at milliseconds to, let's say, hundreds of millisecond type accuracies. Not very flexible, so if you want to say, hey, I want to get more accurate, or I'm willing to spend more bandwidth, let me get more accuracy, you cannot do those kind of things. So it, for example, using an NTP type protocol, it takes an hour to get the error down to 60 microsecond if you're polling at a rate of 16 second, and you don't poll at the rate of 16 second. Most of our laptops and all usually would poll like once a day or something like that. Okay, so if everyone to poll at once 16 second, that traffic will cause problems. Not very energy friendly either. So if you recall this thing, I mean, NTP, this slide we have seen last time, NTP is kind of way out there in terms of its Allen deviation. So it's not that great relative to everything else. So using NTP as your primary frequency source is a bad idea. NTP is really meant to get timing information, and then you rely on local, sort of some good local oscillator for purposes of maintaining the frequency. Okay, so at this point, since other students drifted in, so a couple of things. Number one, I sent out an email on Piazza with for next Monday's presentation topics, and then next Wednesday's presentation topic, next Wednesday and the next week's Wednesday's presentation topics. I will have them hopefully by this evening. So again, the one for 12.8 are finalized. Okay. The other thing is you're all wondering about homework and stuff like that. So what I decided, I'm going to just give one kind of final / homework take home. It will have two components to it. One component would be which you have to do individually, which would be a couple of theoretical problems. You kind of have to solve them, okay, on your own. And the other one would be kind of a team-oriented effort. You can do it in any team size up to 4. And the idea is that using your embed, you'll have to do something all the way to kind of getting information onto a website and back. Okay, so I'm going to send that out. You will not need your BeagleBone. If you have your BeagleBone, you can use that. If you and it might be easier to do with using BeagleBone. If you don't have a BeagleBone, want to use one, you can borrow from me or Raspberry Pi. If you want to, I have a few lying around. Or in the worst case, you can always use your laptop or computer to do it. But basic idea would be there's a couple of things. One is you need multiple embeds. You will have to output signals from the embed whose timings, they need to be time synchronized. Okay, so in the sense that the idea is that embed, you'll have to issue some command to generate some sort of a waveform on these embeds, and these embeds need to be time synchronized. So you have to come up with a simple time synchronization scheme. And the other part is that these embeds have to sense something and send it out to the same backend. So some sort of a website where I can control these things. I can look at the waveform coming from the sensors or events coming from the sensors and control the output side. So that's kind of the nature of the segment. Again, as long as you have access to embeds, you would be good to go. If you have Raspberry Pi or BeagleBone, you could use that as an intermediate. If you don't have it, then borrow one from me. Okay, that's probably the easiest thing. I think the route through the laptop is a little bit clumsier, so I would suggest kind of doing that. Okay. So moving on then.
You have a sort of more detailed explanation.
Yeah, I will. I'll get it out. But just wanted to get the it would be the second half of the finals week, so you'll have to basically come to my lab and show it to me, because you'll have to essentially you sit down with a oscilloscope and just quickly measure it. Okay, so you'll have to give a write-up describing what you did, but then the main thing is testing it in the lab. And if you want to do earlier, set up an earlier time, that's fine.
Is there also a project? Is that finals week? Is that
finals week also? And if you have travel constraints or something like that, let me know. There are two options. You can do it earlier, or you can also, occasionally I have tried this thing and worked out fine. If you're very confident about the polish of your presentation and all, you can record it and send it to me. So that can, or do it over Skype or something. So those are also options. Okay, so so why can we not just use NTP, GPS, and embedded systems? I mean, that's by now hopefully you have gathered that kind of requirements, they don't quite all kind of fit in. I mean, they're either not always everywhere, the power consumption may be too high, too costly. There's nothing quite out there. And the other thing is timing requirements come in varied shapes. Okay, so for example, in an application where I'm trying to localize a target of some form, beamforming, signal processing kind of thing, I need small scope. So it's not like I'm trying to synchronize everything on the planet or even a big network. It's something local that I'm trying to synchronize short lifetime. For the course of the duration on a target, I need to have things synchronized, but I need very high precision, okay, to be able to do this thing. Then there might be examples where I'm kind of doing things over a longer region or a longer lifetime, so kind of requirements kind of change again there. Sometimes I need to just worry about order in which events happen. At other times, I need to know the timestamp of the events. Sometimes I need to do synchronized action, like at time t, do something together, those kind of things. And then finally, accuracies are all over the map. I've listed microsecond to millisecond. Actually, there are examples where you need even like 10 nanosecond type synchronization accuracy. These have to do with like tracking fast-moving objects, airplanes, these kind of things. GPSs and all obviously have to go down to nanosecond. There are examples where things go down to picoseconds, like the CERN group, which is doing subatomic particles and all. So again, accuracies are all over the map. Accuracy comes at the cost of energy, so you don't want to over-design your system. And the other thing is, oftentimes over the lifetime of a system, at different phases, accuracy requirements are kind of different. So they don't sort of quite work out. So what ideally you would like are things which are tunable, things which are can make use of multiple sources of time, are good in energy, have kind of a range, can go down to sort of pretty fine-grained accuracies also, so you can kind of hopefully straddle a wide range. So that has led to kind of quite a bit of work on various approaches to synchronizing network nodes, and of course NTP is a point in space of that. So the basic problem we have is I have a bunch of clocks, nodes with local clocks, and I have some sort of a network. They can talk to each other, and I want to synchronize them. Okay, and at a very crude level, this is a problem of calibration, right? What I have is oscillators which are driving counters. That's the clock at each one of these nodes, and there are three types of synchronization you can imagine. One is three types of calibration. One is you can say, hey, I want to have all the oscillators oscillate at the same frequency, and that's all I care about. And that is useful if I want to simply measure passage of time. So when one node measures a interval of 1 second, like for example, it's measuring the speed of a moving vehicle, then it will come up with the same speed estimate as another node would, because they will measure time at the same rate, but they don't have a common notion of time though. Okay, but their dt over dt over d, their d clock over dt is the same. Second one is that their phases are the same. So they have waveforms. Not only are they common in frequency, but they're also aligned. So if I have square waves, then the square wave edges are aligned at different places, and this is often useful. For example, if you are I don't know, network nodes which are trying to talk to each other, and you want to make sure that your time slots are aligned. Okay, so that you make use of bandwidth efficiently. So that's the second, and as you can imagine, phase alignment is going to be harder than frequency alignment, because phase includes frequency and then additionally edge alignment. And then the final one is time calibration. That is, I want to make sure that the time reported by the counter or whatever variable that I call time at each one of the node is the same, okay, or within certain bound of each other. And of course, time calibration in a way is separate from frequency calibration. If you were to recalibrate time very frequently, right? If very frequently we were to keep recalibrating the time, then it doesn't matter whether my local clocks were drifty or not. But in reality, you cannot resynchronize time very often. So what you do is you synchronize, and then you let things run on a local clock, and then again you synchronize. So the idea is that in most cases, good time synchronization also requires good frequency synchronization. But these are kind of frequent. So time synchronization can therefore be viewed as a calibration problem, and the variable being calibrated is the local clock, some facet of the local clock. So nodes have imperfect local clocks, and by imperfect, what we mean is the following, and I'm using the term clock here to include both the oscillator and the counter. So one is that their starting value may be different, right? Nodes may start at a different time at the very least, and let's say if they always start with the counter value set to 0, just the mere fact that they're starting at different times leads to the initial offset, which is different. Then the clocks have drift, that is, their oscillators are oscillating at different rates. We saw many reasons behind it, temperature and all sort of different things, or merely the fact that these nodes may be using clocks of different types. One may be using a costlier oscillator than the other one, for example. Okay. So if you look at the frequency is the rate at which the clock is changing over time. Okay, so that's what frequency is. And so the clock at any given time is going to be initial offset, which so what I mean by that is at some common point in universal time, what we can say is what were the values of the counters at different nodes. Okay, so there is some initial offset, and then the integral over the frequency between now from t equal to 0 to now, right? I mean, whatever the counter has accumulated, and for purposes out here, we have imagined that the counter doesn't overflow. If it overflows, you're somehow keeping track of that. Okay, so that's what we have. Now, application needs, as you can imagine, they can come in many variety. Some applications may say, hey, what I want to do is I want to take my local counter and map it to a global notion of time. Okay, so in essence, I need to provide a function which reads the local counter and right now and say what is the actual value of right now as agreed upon by my network. Okay, let's say UTC. Mapped time to local time. So what we want to say is, hey, what would be the value of my counter when time is 1 p.m.? Okay, so I would like to know that. The reason is that my software and the lower level stuff is going to operate in terms of my local notion of time, the counter values, right? I might want to say, I want to fire an actuator at 1 p.m. Well, I cannot tell the hardware raise the signal at 1 p.m. I can tell the hardware raise the signal when the counter value is this. So I need to map 1 p.m. to a local counter value. And this might seem simple, but remember, usually we are going for some future time, right? And so we are so like I know right now it's 12:30 p.m. and I say, okay, I want to fire the actuator at 1 p.m. So what would be the counter value at 1 p.m. and then I set the thing to that. The problem though is that between now and 1 p.m. I really have to make some estimate of how my clock will drift. Okay, and I have to be willing to sort of correct for it. Okay, so if I need appropriate high precision, if I don't, if I can live with whatever some tolerance this thing, then I can kind of decide on that counter value and then imagine that something will make sure that that counter value is going to imitate appropriately. And then finally, another type of stuff that we may need is where we say, I received this event from a node. That node put its timestamp on it according to its clock. What was really the timestamp in terms of my clock? So I'm doing a coordinate transformation. I'm basically transforming time from one node's clock to another node's clock. You can think of these two as special cases of this general case if I had one node which was kind of the God node, which knew the global time. Okay? So canonically, and we have seen this kind of thing where clocks drift. So that's sort of part of the problem. So there are two problems basically we have. One is clocks drift, and the other is that it's not easy for us to synchronize our time. Okay, I mean, if you think about the problem of saying that we want to set our clocks, our watches perfectly synchronous so that at some point in time, what the counter, what the one clock is showing as the time and what the other clock is showing as the time should be the same. That's actually not an easy problem to do because the only way we are going to do it is by doing message exchange, and there are all sorts of sources of errors that kick in, which we are going to see shortly. So canonical time sync really boils down to the following, that we need some way of measuring offset between neighbors. Okay, that is, I need to measure what is the offset between the counter or the clock at node I and the clock at node j, and let's call this thing OIJ, offset between ij. And remember, this offset is at a particular value of time, because it's not like we can say that after 1 second the offset at the CIT minus CJT after 1 second will not be the same, because the two clocks, their frequencies may not be identical. Okay, so offset itself is changing over time. And then the idea is that we need to algorithmically somehow estimate what the offset would be at arbitrary points in time. Okay, so I have a sensing problem, that is I sense the offset, and the other is I have a second sensing problem that I've somehow sensed the relative drift, and I use both of these information, I combine them together to then make a prediction about what the offset would be at some arbitrary time in the future, or was at some arbitrary time in the past. Okay. Now, this is a fundamental measurement which we have to do. If I keep measuring this thing again and again, then I can measure the rate at which this is changing, and from that I can derive the drift that my clocks have, right? I mean, if somehow I had a perfect way of measuring the offset, then if I were to measure the offset right now, measure the offset 1 second later, measure the offset again 1 second later, again 1 second later, and I look at that offset measurements, then I can derive the rate at which our two clocks are drifting apart. Okay, so offset measurement is really kind of the fundamental piece. So how does offset measurement kind of take place? Okay, so basic idea in the offset measurement. Let me kind of jump to a slide actually to the future, and I'll come back. Okay, so the basic idea, and one way you can think about measuring the offset is the following. So let's imagine the following exercise: that I have a node which sends out a packet, and it timestamps it according to its local clock as having been sent at T1, and this packet is received at the other node, and it timestamps it as having received at T2 according to its local clock. Okay, so what we can write for this thing is we can say that T2 according to clock B's clock is equal to T1 according to A's clock plus the delay in this process plus the offset between the two, offset between A and B. And let's just focus on that. Okay, looking at just this, I have two unknowns, offset and delay. Obviously, I cannot solve this equation. I know T2, I know T1, but without either knowing the delay or the offset, I cannot solve for the other. Okay, and this is exactly what those broadcast type systems were doing, right? I mean, in the WWVB example, basically the radio station was putting T1, I can obviously, so I get T1, and if I say, hey, delay is very small, then I could basically say T2 equal to T1. Okay, I can always drive the offset to 0 by changing, I can drive the offset to 0, or let me rephrase. I assume delay to be 0 or to be some constant value, and then I can measure the offset and then correct my clock so that my clock is now synchronized. Okay, so that for at that point in time, the offset has been driven down to 0. So I could certainly do that. Is there a way by just doing these you can get a drift? So just this one-way messaging, just sending packets to one party. Can you get the drift out of it? Specifically, can node B learn how its clock is drifting relative to node A's clock?
Constantly measure itself against its own clock and see if the differences.
What do you mean by measure itself against its own clock?
It's constantly keeping its own timestamp of its own clock.
Sure, but that's just according to its local clock, right? Yeah, like, I mean, if just using equation 1, could you measure, and I don't know delay, I don't know the offset, can I measure the drift? And drift specifically refers to d over dt of the offset, right? That's drift.
Delay is constant.
Okay, so let's assume delay is constant, then what? You're on the right track. So let's say delay is constant. And no, you will not answer. So let's assume delay is holds constant. So what's happened? So if delay is constant, so let's say I make this measurement again, right? So I will have a new T2. So let's say call it T2 prime equal to T1 prime plus delay plus offset prime. And then I'll have T2 double prime equal to T1 double prime plus delay plus offset triple prime, right? So I now have multiple measurements of the offset. And if node 1, imagine it is sending out packets every second according to its clock, right? Then what is going to happen is the first packet would be received here at, let's say, sometime t. Next packet, this one sends out the next packet 1 second later, but it may receive it not 1 second later according to its clock, but maybe 1 plus minus some epsilon. And the same process will repeat. So I'll have this, according to this clock, the events are happening 1 second apart, sending events. According to this guy's clock, the reception events are not going to be happening 1 second apart according to its clock. There will be some error in it, and that will give you the ability to measure the drift. Okay. So just one-way messaging can be used two ways, in two possible situations. One is, I know that what the value of delay is, or maybe it's very small. If that's the case, I can immediately use this equation to measure the offset. If I know delay is 0 or that it's below the tolerance of my synchronization, then I can simply say offset is equal to T2 minus T1. Okay, and the receiver can synchronize. If I know that the delay is constant over time, then I can use this thing to measure the drift between the two clocks. Okay, so these are kind of two uses you can do just with a one-directional message exchange. If now we were to introduce a reverse directional message exchange, right? So that's why we said, okay, we can say either delay is too small for us to worry about, or that delay is constant. Okay, but what if we actually want to measure the delay? So what we can do is we can do a bidirectional thing. So now I can repeat the same thing in this direction. So I will have T4, which is the reception time according to A's clock, equal to T3, which is the sending time according to B's clock, plus delay minus offset. Now offset would be in the other direction. That's why there is a minus. Yeah.
In the best way, if you could measure the change of the offset, but you still cannot know the start point of knowing if my time is 2 p.m. and your time.
You cannot. So again, that's what I was saying. So to measure the offset using just equation 1, you have to assume that delay is 0, or delay is smaller than the tolerance that you want in your offset. The second use of this, where I'm sending multiple one-way transactions, the use is for me to measure the drift. But that use does not give me the offset. It's just measuring the change in offset, d offset over dt. Okay, but with this reverse thing, with an additional assumption that the delay in this direction and delay in this direction are the same, now I have two equation, two variables. I can solve it and get an estimate of delay and offset simultaneously. Okay. Now, this assumption that delay is the same is not necessarily true because network paths tend to be asymmetric. But that's the only other way we have. So either we know the delay because we have calibrated it carefully, or we make this assumption. There's no other real kind of way for us to solve this kind of situation. NTP, by the way, uses this kind of a bidirectional handshake. Okay, so it sends out a packet to the server bounces back the packet, you get 4 timestamps, you kind of measure things based on that. Okay, so the problem in each one of these things is also non-determinism. So what if delay changes? Offsets obviously change because the clocks are drifting. And then our ability to measure T1, T2, T3, T4, this is a process of time stamping. So there's some signal changing and you are measuring it by reading, by sort of watching, time stamping it using your local clock. That's also an error-prone process, right? I mean, let's imagine I tell you, tell me precisely when a signal went from 0 to 1. So what would you do? You are going to poll this thing, or your hardware will poll for this thing, and then whenever it went from 0 to 1, you'll take a snapshot of a counter. Well, the problem, right there you have a problem that I cannot give you the time at a granularity finer than my clock. So if my clock is 1 megahertz, I'm limited to a 1 microsecond accuracy right there. Well, that apart, you may also have problems that if depending upon how you implement this thing, I would have additional software delays and all that may happen. So one implementation might be I have a piece of software which is looking at the signal and says, aha, signal went from 0 to 1. My last reading with a 0 was T1. My first reading with a value of 1 is T2. I'll take the average of 2 or something like that and say that's when the signal went up. Well, again, a lot of uncertainty, a lot of error in that process. So we have time stamping errors. We have errors in our model, that is the delay is not constant and certainly not symmetric, and then offsets are changing as well. So going back then, what that means is that at our arsenal we have a few things. I can pre-calibrate delays. Second is I can do a one-way transaction to measure clock drift, and also if I have pre-calibrated delay, then that will also give me and the delay is not changing, then that also gives me offset information. And I can do a two-way handshake to get delay more directly. So typically what happens is that we kind of employ all of these in some combination in a given system. So like for example, one approach might be the following. Once in a while, I measure the offset. And that I do by one of two approaches. One is, right at the very beginning, I can measure the offset. I can measure the delay right at the very beginning. I can calibrate the delay, and then after that point on, I cannot live off them. But let's say I haven't done it. So I have two arbitrary radios who come into each other's neighborhood. First thing they can do is they can do a bunch of bidirectional exchanges, estimate the delay and the offset simultaneously. That's a more costlier process. And then after that, they just try to keep their clocks in the relative drift under control by sending one node sending out periodic messages to the other, the one unidirectional stuff. So I can keep doing it until we realize, hey, our clocks must have drifted far enough apart. Let's do another recalibration, full-blown recalibration. So kind of you can do bidirectional handshake more rarely and a unidirectional handshake more frequently. Another approach could be don't try to do bidirectional thing at all. I basically recalibrate the delays. So I sit down with my radios, I send a message, I receive a message, I develop a model that if these two nodes are D apart, how much is the delay between the two? What is the channel delay? And then I just rely on the one directional messaging because in the one directional messaging, if I know the delay, I can always get the offset. The better your model is to mathematically capture the drift, the farther apart these things could be. If I develop a model as to how my clock is drifting relative to your clock, which is very accurate, then what I can do is I can live off that for a while. So if I know that our clocks will not drift more than 1 ppm over the next hour, and I only need 1 ppm relative drift, then I can try to do the next time I recalibrate a drift is an hour later. So part of the trick out here is that all of this information we kind of assimilate and create a model to say how is the other party behaving relative to my clock, so that I don't have to keep doing this thing again and again very rapidly. Okay, so that's one thing we have in our arsenal. The other part is that if the more accurate we can make your timestamps, the better off we are, because that means with a single measurement, I'm going to get more out of it. So we create a better sensor and we create a better model. These are kind of two things that we bring to bear out here. So let's look at what goes into this thing. Okay, so if you think about how a message goes through a networking stack, so somewhere we have a software which generates a packet. That packet is sent over through some layers of operating system to a communication transmitter. That communication transmitter can be viewed as having two parts to it. One is the actual transmitting circuitry, and the other one is the medium access controller. This medium access controller, basically its job is to buffer the packet until the packet is actually ready to go out over the channel. Okay, and the reason out there is that most of our channels are shared channels, right? So it's not as if, I mean, if you were to simply let the software begin to transmit at arbitrary moments in time, then they will collide with transmissions from other packets. So whether it be Ethernet or Wi-Fi or whatnot, there will be some piece of hardware, software, firmware whose job is to take the packet from the operating system, hang on to that packet, figure out when that packet has to go out, at that point in time, pass it through the modulator radio frequency type circuitry, goes over the channel. On the receive side, it is received again through this kind of a circuitry, and then presumably put in a queue or just handed over to the operating system. So that's basically what it goes on, and this is what we call a sender, this is what we call a receiver. And then the timestamps that we talk about, really ideally what we want T1 and T2 to be is that when packet starts getting sent out here and when the packet is received out here, right? Or alternatively, when packet is sent out here and when the packet is received out here, assuming that Tx and Rx remain constant. Okay, now that also is a big assumption because the algorithms here, Tx and Rx, usually involve some coding and stuff like that. So it's not as if the delays through them is necessarily constant. It could be that the delay may vary a little bit. So best situation for you is when the bits are actually going to the antenna and then actually arrive at the antenna or the two ends of the wire. Okay, so many factors affect that accuracy, but the accuracy with which I can timestamp. But the more control we can exercise over them, the better off we are. Okay, so microcontroller, obviously its frequency and all comes into play. What kind of circuitry you have in the transmitter receiver, they come into play. I've written radio, but the same thing holds true for Ethernet, whatever. What my clock frequency is, because if my clock frequency basic time unit of measurement is slow, then I cannot measure time any better than that. So if I'm trying to measure things using a 1 megahertz clock, 1 microsecond immediately puts the limit right there. What this propagation medium is we've already made some assumptions, right? I mean, we made the assumption that propagation delay is fixed. We made the assumption that propagation delay holds constant over, so propagation delay is constant over time, propagation delay is symmetric, and in some cases we also assume that we know the propagation delay, okay, which all these things kind of come into play. Okay, so what used to be done early on was timestamping out here. This is how NTP works, okay? I mean, the timestamp somewhere out in the stack. But ideally, particularly with the kind of platforms you have in embedded systems and all, you can afford a timestamp at the lower levels. You can timestamp here and timestamp out here. Timestamping here and here is very hard because this is on the other side of the RF circuitry. So this is where timestamping could usually happen. And what happens is that chips that you get, they usually have some sort of a signal that says, hey, I'm actually transmitting now, or hey, I have now received the packet. And the trick is that they put in they monitor the same location in the packet, right? You want to make sure that it's the same location. Usually, it is where the header ends and the payload begins. Okay, so they mark that boundary. So you will see signals like start of frame delimiter or end of frame delimiter. Okay, so these are signals which basically say that, hey, I've recognized the header and payload is starting to be sent now, or hey, I got the header and I'm now receiving payload. Okay, so that's the kind of pin that they would often give off. Radios kind of seek to support good timing. So then really, if I'm able to timestamp at this level, then really the accuracy with which I can do things boils down to the uncertainty in this, right? And this is where, yeah, so you might think that, okay, if I have two devices and they are fixed distance sitting next to each other, then this thing would remain constant. Not so. Partly because these TX and RX themselves are digital circuitries. They have some state machines and all. Depending upon when you are sending the packet, which state the radio was in, there might always be some errors. That's one part of it. The other one is variation. I take one node and send packets through this thing to multiple other nodes, all of the same brand. You will see some variation there. Some of that variation is simply coming from the native frequencies. The clock crystals at those nodes are slightly different, just, even though they claim to be the same. So, so manufacturing variations have come into play as well. So, using these insights, there have been kind of a lot of interesting pieces of work. The other thing to realize is that when what we call as the propagation time, what in reality happens is the following: that at the sender, I'm sending out the packet, and as soon as the first bit of the packet is sent out, after a propagation delay, the receiver will hit it. So in reality, the transmission and reception are kind of overlapping. Okay, the first bit of the transmitter arrives at the receiver pretty quickly, particularly for our short range type stuff. And so the reception and the transmission kind of overlap a little bit as well. The other issues that come into play is that if you are unable to timestamp well at this stage, like for example, let's imagine something like the following. There are two ways I could timestamp this. So my radio sent me the signal saying SFD went high. Okay, I want to timestamp that. So one way could be that I can tie it to an interrupt handler, and then the interrupt fires, and within the interrupt handler, I'm going to read the read a clock, read a counter, and say, hey, that's the timestamp. What problem do you see with that? So I'm trying to timestamp this signal which is saying packet is being transmitted. I tied it to an interrupt, let the interrupt handler fire. Within the interrupt handler, I read the timestamp. What sources of error do you see in that?
The delay from the interrupt fire and the process.
Okay, and what would affect that delay?
You read the counter after some.
Yeah, but what affects that delay? What all things go on? So let's say the very first instruction of my interrupt handler is read the counter. Okay, but I'm basically asserting that even up to getting to that point, there are delays. What are those delays? What happens in an interrupt, from a processor? What happens when it handles an interrupt? Right, so it has to save the stack, right? So some delay is going to go into that. Now there are some specialized processors where they carry two register banks. So the interrupt is very rapid. As soon as they go into the interrupt, they start using the other register bank, and so they never have to save the registers. Okay, but there would still be a few clock cycle delays. Most processors don't do that. There is an explicit saving the register phase which is going to happen. Okay, so that's one issue. What else can confound this picture? So that's one, and you could argue that I can characterize it. The problem is its delay is often very variable, but okay, so that's one source of problem. What's the other source of problem? The second source of problem.
The interrupt will not fire at that time because of some other processing of the other interrupt.
Right, some other entity may have disabled it, which is almost every operating system. There are times in which it disables the interrupt. Okay, in fact, processors which can work without disabling the interrupt operating systems and software which do not ever disable the interrupt are tricky, okay, because you have issues of nested interrupts and things like that and all, okay. So that's the other. So there are two sources of problem. One is interrupt may be disabled, and the other is, in any case, if it was not disabled, some initial work has to be done whose delay you need to kind of characterize, okay. So this approach still has some lingering uncertainty. So how would you do it more accurately? So recall the kind of timers and all I had talked last time around, which most embedded processors have. Would any of those help you out? So one of the capabilities I had mentioned as an example with the LP1768, but it's pretty much in every processor, including your embed, which is they have this notion of timer capture. That is, in the hardware unit, there you could assign a pin whose job is that whenever that pin fires, then the value of the current value of a counter is copied into the register, and that happens immediately. No software intervention. It's almost like you have a dedicated hardwired interrupt handler for that thing, okay, whose sole job is to take a snapshot of the counter. Okay, and as long as you can then read it out before the next time it comes, you're good to go. Okay, so the preferred way of time stamping, therefore, is not to use the interrupt handler, but to rather use this shadow capture, shadow register or capture register, as they're called.
But how to specify the criteria at which this?
How to what?
How to specify the criteria at which this timer capture will happen?
The criterion would be by tying the pin. So you would tie, so associated with the timer would be some pins that timer is able to monitor. So you will have to make sure that the relevant signal of your radio is feeding into one of those pins, and then the processor would have some sort of a control register in which you specify that whenever that pin has a transition, then this timer's value should be saved into the shadow register, okay. And then the only remaining thing you have to worry about is that before the next packet is sent out and that the transition happens again, you have read this thing out, basically, okay.
I think we also need to handle the case that we have two separate chips, the RF and the processor. And the clocking you are talking about is which clock? You have to feed the clock from the processor to the RF to take a shadow from it.
No. So from the radio or whatever, the transmitter, there is some signal coming out saying, hey, I'm just starting sending the packet, or hey, I just received the packet. Okay, so you take this pin and you tie it to the particular GPIO pin, which the timer is able to monitor.
So you will do all the stuff at the processor with the microcontroller level, not the RF.
So all the RF is doing is to generate the signal, right? Generate the signal saying the packet is going out or the packet came in. Okay, and then the microprocessor is or the timer unit of the microprocessor is configured so that whenever that signal comes, you take capture. Okay, no interrupt handling is involved directly in this case. Okay, in the sense that instead of reading the timer inside the interrupt handler, you let the hardware handle this thing. And almost any microcontroller nowadays will provide you at least with a couple of counters with this kind of capability. Okay, that is where you can do this thing. So that's one of the ways you can get fine accuracy of time stamping, basically. Okay, so using these kind of techniques, one can do things. So things have advanced quite a bit. I mean, it used to be you timestamp up here, and then all the buffering delay will come into play, to now where I can do stuff at the lower level. Now, of course, what the problem comes is sometimes your radios and all may not give you a signal out here. Okay, then of course you're stuck. Then you have to kind of do it out there. Radios and Ethernet chips and all, they try to be smarter. So they usually like to put MAC inside the processor. But then usually, and in this MAC is usually a queue. So there's stuff going on inside the processor, and then all you know is when you handed it over to the MAC, you never know when the packet actually went out. So the radio has to provide some pin for doing it. The more enlightened manufacturers like TI and all usually provide that pin, Atmel, but many don't. In which case you have to figure it out somehow. I mean, life becomes harder in that case. Yeah.
Isn't some RF that
You could. I mean, certainly it's possible that the radios may have their own timer and they can do it. The problem though is, I mean, usually I haven't seen this thing, and the problem, all it is doing is moving a piece of hardware from the processor side to the radio side. It doesn't really kind of buy you much, but you could imagine. So the point Amr is making is that there are perhaps some radios and all which maintain their own counter internally, and they timestamp according to that. And they could do it. The only thing is, I think they make life a little bit harder for you to deal with, because then you have to worry about keeping your processor time in sync with the time inside that radio. Okay, so you have an additional layer of synchronization.
But I'm afraid of this signaling to the bin and preparing the bin to signal. I don't know how much it delay signal and trigger the bin. I could have packet like that. I don't know the delay sending the bin from RF to.
Okay, so good point. So what you're saying is, hey, I don't know what the delay is between the packet actually going out versus the transmitter saying I'm sending the packet. Okay, that's an uncertainty one also has to deal with. And these are all things one can study and characterize. And I'll have some plots showing that, I mean, the radios do have significant variation in the delay for all these factors, because radios inside them have state machines. And also, if you look at these algorithms, sometimes the algorithms are data dependent also. Like if the packet has a series of zeros, they may behave differently than the packet has a random value, because, or depending upon the channel condition, things may vary, like more coding, decoding needs to be done. So things can get tricky. Modern radios and Ethernets and whatnot, they change the rate dynamically depending upon channel conditions. So there are complications, no doubt. Okay, so there are radio chips where these kind of signals are given out. Okay, some radio chips are so dumb that they really don't do anything, in which case they literally kind of expect you to feed them bit by bit by bit, in which case you can kind of mark it yourself. But the smarter radios, which have stuff built into them and all, they basically usually will give out some sort of a signal giving out. So this is start of frame delimiter signal, which the TI chips give out. Okay, so the idea is that you can monitor this. This is sent out when at a particular point in the receive packet. Okay. Now, despite all of this, you play all these tricks and all, you'll still see variation. So this is an experiment where I have a radio transmitter and two radio receivers, identical ones, so the same brand radio and everything. And all we are doing is that we are sending out the packet, we are measuring the timestamp out here, and then we are receiving the packet here and receiving the packet here, same packet. Packet received here, packet received out here. We are timestamping it here and timestamping it out here. Now, of course, these clocks have some arbitrary offset between them, so we can zero them out. Okay, so take the mean and compensate them. So whatever spread is remaining is really saying the variation in the delay. So what you see out here is transmission TX to RX1 and TX to RX2. Okay, so what you see out here is that across a bunch of experiments, the gap, a bunch of packet transmissions, the packet looks something like this. So it's around 3 microseconds, and then there is a spread from 3.05 to 3.25. Okay, so what it's saying is that there is roughly a spread of around 0.2 microsecond or so between the different runs. Now, the source of this 0.2 microsecond, it's very unlikely to be anything in the channel itself. It's just close by nodes over a radio link, so that's not the issue. That is, the air part is not the issue, so it has to be kind of a radio part. Okay, and anything else that sort of, in this particular case, oscilloscope is being used to kind of measure the time thing, so we have a very high quality time measurement, so it's not quantization error on our side. It is basically processing within the radio, which is the culprit. And you would see this is with the other one, and the final thing is receiver 1 to receiver 2, this another one. So there's a variation, and then no pair are identical either. Okay, I mean, they're roughly similar but not exactly the same. So there's always some gap or other. So the difference between these two is what is shown out there. Again, kind of a major spread out there. So what it says is that really this is the bottleneck in terms of how accurate you can time sync. That is, you need more deterministic communication medium and communication chips to kind of make this thing happen. Now, the other thing looking at this thing is you see that they are kind of Gaussian looking. Okay, and Gaussian is good because what that means is I can make multiple measurements and average them out and cancel the error, right? So essentially I have a sensor in this case, which is where offset measurement and whatnot. I have a sensor which is being subjected to this Gaussian noise, and I can, by taking repeated measurements, I can cancel that thing out. Okay, so error can be reduced statistically by sending multiple exchanges and then doing an averaging over it. Now, there is a problem in this thing. So let's imagine I sent out a packet. A second later, I sent out another packet. Later, I sent out another packet, and so on and so forth. And I'm measuring the drift. Okay, so my offset is changing, and with that changing offset, I can measure a drift. But the problem is drift is also changing, right? I mean, if let's say if I were to send these probes 1 hour apart, it's quite certain the drift has changed. If on the other hand I sent these packets just 10 milliseconds apart, it's unlikely that the drift would have changed much. So I'm actually trying to track a moving target, right? I mean, if one of the earlier slides, I had a bunch of nodes and the clocks were drifting over time at different rates. So not only are clocks drifting, but the drift itself changes over time because of temperature conditions. That could be one node is outside, one node is inside, is being subjected to different temperatures and stuff like that. So what we have to worry about is we cannot simply do an averaging. We have to do some sort of a curve fitting over time, taking this thing into account. So let me again kind of jump a few slides ahead. Let's see. So kind of the idea is that if I were to measure this offset, I'm going to see I'll get some measurement points, okay, about my offset, and then I would do some sort of curve fitting over it. And if this thing is over a short enough time interval, that is, I'm doing these measurements relatively rapidly, then a very reasonable assumption to make is that the drift is constant. That is, or drift is changing linearly, which is the more typical arrangement which is made. Okay, so basically the idea is you kind of do a straight linear regression for this thing. Okay, and then over a time window. So basically what happens is you basically say that I'm going to keep making these offset measurements, and I'll look at relatively short time windows, and I'm going to fit a straight line over it, and I'm basically going to say that my clock is changing relative to the other clock according to that linear model for some reasonable time interval. And then over longer time horizons, I refit this curve. Okay, so temperatures, usually temperature changes on order of minutes to hours. So you can probably get by with a linear model for some number of minutes to perhaps even, if you are lucky, perhaps a few hours, and then you kind of recalibrate the whole thing. So piecewise linear kind of a model one could use. Or one could use more sophisticated models. You can try fitting a higher order polynomial and all to this thing also if you have a better understanding of the drift. So the main idea then is that I'm not simply going back out here. Even though Gaussian is good, I cannot simply average the readings which were taken far apart in time. I have to actually fit some sort of a curve to that to take into account the fact that that has drift happening and that drift itself may be changing. So piecewise linear is the most common one which is used. Why?
Can you go back one slide? Is this the part of the so-called additive Gaussian white noise we talk about in communications classes?
No, this is the Gaussian noise in my delay. So no, it's not additive white Gaussian noise that you see in the communication process. No, but the noise is of similar nature. So there, the additive white Gaussian noise is affecting the value of what you are transmitting, right? Okay, the zeros, ones, or whatever. Here, the strength of the signal. Here, it is referring to the time that we are transmitting. But point about is that we in EE or whatever in math, we like Gaussian because Gaussian can be dealt with nicely. Okay, so what all of these things then lead to is different ways of organizing the process of synchronization, and there are many of them which have been done. So one common approach, and this was very popular when we did not have low-level timestamping nailed down. Okay, so the basic idea out here is that there is a sender which is going to send out a packet, and we don't ask the sender to timestamp anything. Okay, so and this was great because usually in early days, it was difficult to timestamp accurately on the outgoing side, and the reason was that we had to timestamp it before the MAC layer, and therefore buffering delay in the MAC layer mattered. On the receive side, you could still get decent timestamp. So the idea out here is the sender sends out a packet, specially marked packet, but it doesn't timestamp it. These packets are received at bunch of receivers, all in the range of this transmitter, and they all timestamp it. So this guy may say, hey, I saw it at t equal to 4 according to my clock. This guy may say, hey, I saw it at t equal to 5 according to my clock, and other nodes will do the same thing. So it's kind of like the bell rang, and then each one of us looks at the watch and say, oh, okay, it's t, whatever, 1 p.m. on my thing, your clock watch maybe 1 p.m. 1 second, and so forth. And then we'll all talk to each other. And the idea is, I'll say, hey, I received at 1 p.m. You say, nope, I received at 1 p.m. 1 second. That information tells me that our clocks are 1 second apart because we all heard the same common event, but we heard it at different times according to our clock, so we are going to exchange. So that's basically what happens. So earliest idea on this thing was kind of back in 90s, and then there was a lot of work here at UCLA and CS department and this thing. These are called so-called RX type scheme as how I like to label them. So receiver. So the main thing out here is that uncertainty of delay on the sender side doesn't matter because we are not relying on its timestamp at all. All we care about is that we should be able to timestamp accurately on the receive side and then exchange those messages, okay, and then reconcile the thing. So at the end of so everyone hears this common message, and then there's a message exchange goes on, at the end of which everyone on the receiver know their mutual offsets. Now, one thing to bear in mind is a few things to sort of bear in mind out here. Number one, all this reconciliation takes time. So we all heard the packet and timestamped it, but then we are exchanging messages, and by the time we learn the offset, it's already old information, right? I mean, so for example, let's say I heard the packet, and there are 10 nodes. They need to all talk with each other. So maybe what they do is they send their information to a single node, and then they receive it back. Well, doing that is going to require 10 plus 1, 11 messages, okay? If you look at a radio, 11 messages is probably going to be maybe 15, 20 milliseconds of communication time. And so by the time nodes get to know the offset, they're knowing the offset as it was some time ago, okay, because the reconciliation kind of takes time. So this is something to keep in mind. The other part is that there is an assumption being made out here in terms of the offset. So I'm basically saying that if these two nodes exchange their messages, they measure their offset. What is the assumption? Huh?
They are the same.
They're the same what?
Their hardware and their stuff are the
No,
same.
no, let's say they are able to accurately timestamp.
The delay is the same.
Delay is the same, right? I mean, so what if one node was very close to the transmitter and another node was farther away, right? So propagation delay, or at least 2 times the propagation delay, because then it happen to be on the other two sides, right? I'm sorry, not that. The difference in propagation delay kind of will come into play out there. Okay, so that becomes an issue if you're working with high latency type networks and all, like underwater or regular internet and all. So that becomes an issue out there. But the main thing that this thing combats is that it doesn't have to worry about uncertainty of timestamping on the sender side. Sender side doesn't have to timestamp at all. And in fact, you don't even need a sender. This trick can be done using any other thing that all receivers can send. It could be a loud sound. It could be a flash of light. It could be any common event that all the sensors have the ability to sense and uniquely identify. The reason a radio packet works is because we can embed a sequence number in the radio packet, so therefore you can say, hey, I saw the packet of this type with sequence number blah blah blah, and that's the timestamp. Okay, so it's easier done with radio packets, but it could be anything. Okay, so the other scheme then, so that scheme was where we were unable to precisely timestamp on the sender side. But what if we are able to timestamp? And as I showed that with lower level timestamping and all, we could. Then we can go to this bidirectional scheme. This is what NTP uses and some other schemes have used. Kind of the basic idea being that through this bidirectional exchange, I actually measure the delay also. Okay. So the assumption out here being made is that the delay is symmetric, number one. Second assumption being made is that delay is constant at least over the short time span, right? That is by the time the written packet is sent out. And that's probably a reasonable assumption, but the asymmetry is usually the problem. That is, it's very hard to have in networks delays that are symmetric. In case of wireless situations like sensor nodes talking to each other over radio links, that's probably a fair assumption. But like, for example, if you take your cellular phones, that's not at all true. Or if you look at your cable modems at home or DSL modems or these kind of things, it is not true at all. Or if you're going over a network, it is not true at all. So big part of the issue that NTP is not as accurate is because it is dealing with network delays which are pretty flaky. And but this kind of thing will work fine if you, I mean, like I said, you have peer-to-peer communication between nodes. Okay, so there, the symmetry assumption is a reasonable one. Why is it that I said that cellular telephones, the delays are not symmetric? Why do you think that's the case? Firstly, any intuition as to which delay would be higher? Cellular phones. I said the delays are a lot in cellular phones, and they're asymmetric. Yeah.
Are you saying that the delay from the transmitter to the cell phone and back?
No.
What?
No. So I'm basically saying that if I'm sending a packet out over the cellular link versus I'm receiving a packet, the downlink delay versus the uplink delays are not the same. Tend to be very different.
I think from handset to the base station will take more time because the transmission power will be less.
No, nothing to do with transmission power, but it is handset to the base station is higher because you're competing for bandwidth. So you have to go through a medium access control process and all. Whereas on the downlink side, the base station kind of sends it out and the line is clear. Okay, so usually delays, and whether the same logic why your cable modems at home, again, both the bandwidth and the delay is much worse outgoing than incoming. So asymmetry is part of life, and obviously that assumption breaks down. But in situations where, let's say, I have peer-to-peer networking and all that kind of situation, the symmetry can hold true. Okay, so between these two, there is another aspect which comes in out here is that the way the equations work out. Let's see. I don't. Okay. Yeah. Oh, I have. If you see on the equations out there, there's a factor of 2 down there. Divide by 2. So what that means is that any uncertainty in these things also gets divided by 2. Okay. So uncertainty in timing and all gets divided by 2, or any other forms of uncertainty also get divided by 2. Whereas in this particular case, that doesn't happen. And it has a peculiar consequence that in situations like underwater networks and all, where you are doing acoustic transmissions, that divide by 2 helps a lot, these type of schemes, whereas these guys face the full brunt of the error. So you would see that in many situations, particularly underwater, these bidirectional schemes do much better than these unidirectional schemes, independent of another track. So which, I guess the message I'm trying to give is which one is better and which one is not depends upon a lot of circumstances. Your technology for timestamping, the precise situation you are in, bidirectional versus unidirectional, and the type of signaling that you are doing. But perhaps the most influential time synchronization protocol when it comes to wireless time sync and all is something called FTSP, sort of Vanderbilt. And what they do is the following. So it's actually along this line of one directional, or maybe the best way of saying is it does just this part of the step, but it calibrates delay very, very accurately beforehand. Okay, so what it does is that it takes these radios, pre-calibrates them, and comes up with a model for the delay, and then it subtracts them out. And then they achieve like sub-microsecond type accuracy, or kind of order of a microsecond type accuracy. And then a lot of work has built on top of this thing. So one issue that you also face is, let's imagine I have a chain of nodes. Node 1 is synchronizing with node 2, node 2 with 3, 3 with 4, 4 to 5. I look at the 2 nodes at the end. They would normally, if you don't do it carefully, the error would build up over the network. So I would synchronize tightly with my 1-hop neighbors, less so with 2-hop neighbors, even less so with 3-hop neighbors, and so on and so forth. there have been some schemes which have been proposed which make use of some interesting characteristics of radios, which actually make the error growth kind of flatten them out so that you don't take a hit with the network diameter. So what FTSP does is that as the packet transits through, they timestamp it multiple times. So they keep track of each and every delay in the node. So kind of the idea is the following, that let's say I have a root node, it sends out a packet, it timestamps it, and they have calibrated pairs of nodes. So this packet is now received by the one hop neighbor. The one hop neighbor receives that packet, timestamps it on the reception side, then transmits it again. So it goes to the second hop neighbor. But some time has been spent at this intermediate node, and that time is something also that you need to keep track of. So what it does is, as the packet is transitioning through, it actually timestamps this thing, and it has a sense of how much time elapsed along the way at different stages. So that by the time you reach the desired node, you actually can compensate for all these things otherwise. So what? So the non-deterministic time which intermediate nodes are spending handling this packet, you also kind of compensate for it by keeping track of this timestamp. So FTSP kind of is pretty much it's a pretty old protocol, but it did its job very well, very influential. And the only thing is, the only situation it kind of fails out is really when you are doing underwater type thing, because this is a one-way protocol and the uncertainty in propagation delays kill it in certain settings. Okay, so this is just some experimentation results. I'm going to kind of skip over them. Okay. Then the part comes about is that a lot of these things are affected by the clock drift is changing over time. So I mentioned that I can do time stamping. So I can do short-term clock modeling using a linear estimator. But then over longer time duration, there is the drift itself changes. So what these schemes like FTSP and others do is that they basically take the offset measurements and they keep over a recent window of time, they maintain a model of the clock drift and they project it out. And they basically, using this projection out, you can now do things like, what should be the time I should next recalibrate? So if I see that my clock is not drifting much relative to my neighbor, then I can schedule the next resynchronization time much farther out in future than otherwise. Now FTSP doesn't do it, but you can imagine doing it. So I can learn that this neighbor and my neighbor, our clocks are pretty good because maybe we are sitting in the same room. And therefore, I need to resynchronize with this neighbor much less so than, for example, let's say a neighbor which is sitting out in the sun and therefore is drifting a lot more, and therefore I need to resynchronize with that neighbor more frequently. So if relatively speaking, a pair of nodes have good clocks versus bad clocks, that can decide by using this kind of a model, you can then decide when should I do next. If I see this model is changing very rapidly, that means we are drifting much more often, then I should recalibrate more frequently. So you can do an adaptive kind of an approach out there as well. I'm going to skip some slides out here. High latency communication. So this is the underwater scenario. So in high latency communication, a problem that happens is the following. Delays are very large in the channel. Variations in delays are very large in the channel. And as a consequence, what happens is that firstly, bidirectional schemes which have a factor of 2 advantage perform better. But the other part is that even within the handshake, so the bidirectional schemes, there is one message going one way, the other message going the other way. Even within that time, the drift can change quite significantly because we are relying on a very slow communication. So sound travels at, in water, I think it's 1500 meters per second or something like that. So by the time the reverse message is coming back, the clock has drifted significantly, even with this linear drift kind of model in place. So what ends up happening is that in the equations for that we previously had, let me go back. In this equation, these two equations are no longer correct. Offset is not the same between the two. So how can you correct for that? So what I'm basically saying is that our signaling mechanism is so slow that this packet communication takes place much after this packet communication, and therefore the offset, the assumption that the offset remain the same is no longer true. So how could you correct for that?
Is the rate of change in offset constant?
Or you can measure the drift, right? Yeah, so you're on the right track. So basically, remember, we're talking about drift. Drift is nothing but a model of change in rate of change of offset, right? So I can say that this, instead of using this offset, I can say offset plus a term which is T3 minus T2 times the drift, right? And I can add that, and I would have estimated drift previously, so I can use that, and I know that the drift changes, but the drift doesn't change that rapidly, right? So my offset has changed because time has elapsed because of the drift, but change of drift, the d over dt of the drift is slower. And so I kind of rely on that. So I have a drift model and I can compensate for this. So for underwater type usage, so this was work out of USC, what they did was they took this basic scheme, but then they added terms out here which is indicating that this offset is no longer the same as this offset. This offset has an additional term which corresponds to how much my offset would have changed, and that basically means between T3 and T2. So T3 minus T2 multiplied by whatever my latest estimate of the drift is. Okay, and you kind of keep revising this process. So by keeping track of, by having a good model of the clock, you can do some pretty amazing thing. NTP does the same kind of stuff also. So NTP maintains locally a computational model of the clock of as to how my clock, how the host, client host clock is drifting relative to the stable clock, and it updates this thing. They actually use even more sophisticated techniques than just linear regression kind of stuff and all. They use Kalman filters, these sort of things, much more sophisticated. But kind of basic idea is that you develop a computational model of the non-idealities of your clock, and you use that to correct all the transactions. And using these kind of techniques, kind of the best schemes out there, like I said, are able to achieve some pretty amazing amazing numbers. You can also take into account temperature kind of effects. So you can have a temperature sensor, which you can then use to compensate for the timing as well. Okay, so let's see. What else do I want to cover on this one? So high latency. Yeah, so this is key. Next up, IEEE 1588. So IEEE 1588 is a relatively new standard which came out for very high precision timing to be done over local area networks. Okay, so it came out in 2008. There's a more recent version out here as well, and kind of main objective was to define a protocol which can do very precise synchronization and can be implemented on kind of local area network kind of thing. So this is intended for like factory automation or kind of Wi-Fi usages and these kind of stuff. And a basic strategy in this thing, so the couple of things that they kind of realized. So one is, what they realized was that it is very hard. Let me kind of go back slides again. To make this magic happen, one thing we need to be able to do is, remember, we are going to be doing the calculation here. So T1, T2, T3, T4, we'll solve the equation out here. One thing that I need to somehow do is that when B is sending the packet, it should carry T3 in it. So I'm sending a packet, I'm timestamping the packet, and I'm carrying the timestamp in the packet, right? And that's a pretty hard thing to pull off if you think about it, right? I mean, so I'm timestamping and inserting the timestamp in the packet itself, presumably at the end. Not all radios will let you do that, because the moment you do it, you may have to perhaps recalculate the CRC. Maybe the radio doesn't like, will let you even append something to the packet. So complications come out of that. And they kind of realized that this is sort of a problem. Unless you have very low level visibility into the radio, you cannot really include the timestamp as part of the packet. So what 1588 did is they switched to a slightly different model. So what they do is they send out a packet, and then the timestamp follows in a subsequent packet. Okay, so I think I ended up messing this figure. But what ends up happening in this particular system? So there's the other side which I think I chopped off in the process of forming this image. So what happens is that there's a master side, there's a slave side. The master side sends out a sync packet and then follows up immediately in which another packet which actually carries a timestamp of that sync packet, so that it's sent out separately. What this guy does is, then it sends another message, and the idea is the purpose of this message is to get the delay information, and then this guy responds with it with an information containing when the packet was received. So in essence, what we have is we have T1, which is actually the sync message whose arrival time this guy would know, but T1 itself is sent in a subsequent packet, and then this guy sends out a packet at T3. And then this guy receives it at T4, and then T4 is sent out this way. So in this case, what's happening is there are 4 messages going on. At the end of which, the slave on the right hand side would have T1, which arrives in this packet, would have T2, which it knows because it measured, it would have T3, which it knows it measured, and then T4, which arrived in this packet. So it will have T1, T2, T3, T4, same type of equations it would apply, but it's sending 4 messages instead of 2. Okay, and there are 2 reasons that this thing is happening. One is they are recognizing the fact that it's very hard to send this packet and carry T1 in it. And the other part is that here the initiator versus who gets to know the offset and who's initiating the process is different. In the first scheme that we had, node A was starting the process, and at the end of the process, node A had all the information. In this case, a central guy, a master, is starting the process, so it will send out the sync message to everyone. Okay. Now, of course, the advantage out here is this sync message could be broadcast. So it's not per node that I have to do. I can basically send it out, and this message can also be broadcast. So I can broadcast the initial message, I can broadcast the follow-on message, and then the other nodes can do a pairwise thing. So the real cost of this thing in a network of n nodes is 2 plus 2n. Right? You can do a similar optimization of the original scheme also. You can imagine the first message going out was common, was broadcast, and then the reverse message was sent individually by the node. So there the cost would have been n plus 1. In case of the receiver-receiver thing, there was a single broadcast message, and then all the other nodes had to reconcile. So that would have been 1 broadcast message, n messages to collect the timestamp, and 1 message to broadcast the offset factor. So it would have been n plus 2. So each one of these schemes could work better if you were to could be made more efficient if you make use of the broadcasting. 1588 kind of adopts this thing. It's a standard, and you can now buy network card and Ethernet chips and all which support 1588. In effect, what they do is they do the timestamping which is required by 1588. Original Ethernet boards and all did not have any timestamping capability. So any timestamping was done by the operating system, and that's why things were less accurate. That is why NTP is as inaccurate as it is, because within the Ethernet packet there is buffering and all that. Now these kind of schemes, 1588 compliant Ethernet take care of it. Pretty much every modern Ethernet chip, likely in your laptops and desktops, probably has 1588 in it. It's probably not being used because you do need the specialized software support for it, but the chips themselves kind of exist. So let's stop at this stage. We'll pick up the remaining thread on Wednesday. So again, to repeat the announcement, so number 1, I sent out the next week's Monday's project presentation topics. Next week, Wednesday's presentation topics I should have by this evening. There would be a single kind of homework / final with 2 components to it. One is individually done theoretical component, and one is a programming problem which you can do in up to teams of 4. And you can use any technology software-wise, many of which we kind of heard about in